get into this. Okay, so one of the things I'm going to mention, I'll put this in chat as well. You had the link. So this is the sheet that I just put into chat, and we'll bring it up from time to time. This has all the proofs of the theorems, excuse me, not proofs, the theorems that we're going to be using to show convergence and divergence. It's a 2-page document. And every time we do a test, I'll show you where it is on here. Some of this stuff we will not get to today. For instance, with the stuff with power series, we won't see that till next week. But we'll talk about all of these tests today. And every time we do on the slides, I'll come over here and show you where they are on the sheet. Use this sheet as you work on homework. You will have this exact sheet available to you for the final exam. Okay, so by all means, practice with this sheet. Okay, let's dive in and go through all these tests, because there's a lot of them, and how we use them and when to use which one. All right. So we've started moving into series, which is when we sum up the terms of a sequence. Now, if we call it S sub n, what we have is a finite series, maybe the first 10 terms or the first 20 terms. Well, the partial sums create a sequence themselves, S1, S2. So these are all partial sums. So this would be the sum of the first term, the sum of the first 2 terms, sum of the first n terms. Those sums create their own sequence. And that sequence converges if those terms go to some limit. Same idea as convergence of a sequence from 8.1. Now, our goal in these next couple sections is to figure out when these converge or diverge. We'll actually use those facts when we start looking at power series in 8.5 and 8.6 in Taylor series. But for right now, our goal is just to prove whether we have a convergent or divergent series. We've already looked at geometric series, and we know that those converge when we have a common ratio less than 1. And in fact, with geometric series, we can actually find out what they converge to. Now, these are just examples of some series, okay? We will at some point today investigate all 3 of these as to whether they converge and diverge or why. So let's focus on when a series converges and when it diverges. So if a series converges, it goes to some finite sum S. This idea is very similar, and you're going to see how similar in a couple of slides, to our improper integrals. Remember, we had improper integrals where the upper limit was infinity. That did not mean that the integral did not exist. We had some more work to do. Same thing goes on with series. Just because there's infinitely many terms doesn't mean it diverges. So let's start off with this series from our other page. So first thing you're going to want to do when you get a series is to determine what kind of series it is, or at least what kind of series it looks like. When the general term is given by an exponential function, we have a geometric series. So if we want to find, first off, we want to decide if this thing converges or diverges. So 0 to infinity of 1/2 to the n. This is a geometric series. Well, geometric series converge if the common ratio, its absolute value, is less than 1. So this thing converges. Well, let's go over to our sheet here. Infinite geometric series. Notice here's the base of our geometric. Zoom in on that just a little more so you can see what I'm pointing at. X is the base for our common ratio. If that common ratio is less than 1, its absolute value, then the series converges, and we can find what it converges to, the first term over 1 minus the common ratio. So our first term is going to be when we put in 0 for n. So a sub 1 is 1, because 1/2 to the 0 is 1. So not only can we say it converges, we can say that the sum is equal to 1 over 1 minus 1/2, or 1 divided by 1/2, which is 2. So that is the sum of this geometric series, and it's convergent. As I go through these, guys, if you have any questions, feel free to drop a question in chat or turn on your mic and let me know. And I'll take pauses every now and again to double check. You know, this is something we've done before. This isn't new, but now we're going to move out and generalize. Now, there's something very important going on with the sequence. The sequence is just the 1/2 piece to the end. And this is a very important part of these needing these. We need to have these series converge. Well, the limit of the sequence as n goes to infinity, well, what's going to happen, the denominator is going to grow, the numerator is just going to stay 1, so this equals 0. So the terms of the sequence eventually go to 0. What we're going to find is that's a necessary but not sufficient condition for a series to converge. And I just want to be very explicit that I am switching between the terms sequence and series. The sequence, the general term is 1/2 to the n. The series has the summation and is adding up the terms. So here's the theorem. If we have a convergent series, then we know the sequence goes to 0. Now, if we just think about that, why that makes sense, remember, we have an infinite series. If we want the sum to converge, eventually we have to be adding 0. You know, if our sequence goes to 1 as n goes to infinity, well, then eventually we're infinitely adding 1. And there's no way that that sum can converge. It's going to go to infinity. So we need the terms to go to 0. Now, here's how we're going to use it more often. If the sequence does not go to 0, then we know the series diverges. All right. Now, I want to show you where this is on the sheet. Convergence properties of series right here. If the limit does not go to 0, then it diverges. Let me show you real quick how easy this one is to use. It's an easy one to use, and it should be one of our first tests, guys, before we go on to anything else, because if the sequence does not go to 0, we're done. It diverges. Let's take this series here. So we're going to look at the series from n equals 0 to infinity of 5 plus e to the negative n over 5 minus e to the negative n. And so what you do is you take the limit. Let's make that a little bit cleaner. You take the limit as n goes to infinity of just the sequence. You don't worry about the sum. Plus e to the negative n over 5 minus e to the negative n. Now, e to the negative n goes to 0 as n goes to infinity. So what we end up with is 5 plus 0 over 5 minus 0. This is basically just 1, so we end up with 5 plus 1, or 6. Well, that clearly does not equal 0. So our series is divergent. And we always want to give credit to what we use. I like to call this thing the Divergence Theorem. It's not its official name, but you can use it as, say, a convergent property of series. I'm going to call it the Divergence Theorem. And you're going to see I use a lot of acronyms in this section because we do a lot of writing on this course. So we always want to say, we always want to show why. We need to show the hypothesis is met. So that's step 1 right there. Then we need to show our conclusion that it's divergent and which of our tests we used. Okay. Questions about this? So DT is just standing for divergence test or divergent. Yeah, let's just call it divergence test. Maybe not theorem. Feel a little better about that. Divergence test. Okay. So again, here's the theorem. And this is great, but it's not going to prove convergence or divergence. What we can take from it, though, is if the sequence does not go to 0, then the series has to diverge. And we don't have to do any more work than that. So that's why I'm saying this could always be your first step. Make sure that that sequence goes to 0. If it does go to 0, then you move on to the next test. If it does not, you're done. Now here, this is very important. It is not enough to show that the sequence goes to 0 to show a series is convergent. And the perfect example is going to be this guy 1 over n. All right. We're going to take a look at this series. This was the last one from that first slide too. So we'll get into all of them. And again, guys, if you have questions as we go through this stuff, feel free to ask. We're going to look at this series, excuse me, from n equals 1 to infinity of 1 over n. So we're going to look at this series. Now, right off the bat, if we wanted to run our divergence test, we would do the limit as n goes to infinity of 1 over n. That is 0. That passes our divergence test. So it's not enough information. We have to go to the next test. Well, I'm going to give you a pretty interesting little argument here, and then we'll formalize it. All right. This is the graph of 1 over x. Now, what I want to do, and let's say 1 is right here. What I'm going to do is do our basically our our left-hand rule on this. Because if we let each of these spaces be 1, there's 3, there's 4, 5, so on and so forth, right? This is our right-hand rule, and we're letting our delta x be 1. There's a very specific reason we're doing this. Remember, this function is 1 over x, and the height of this block is 1. The height of this block is a half. Height of this block is 1/3. So on and so forth. Those are the first few terms of this series. N equals 1 to infinity of 1 over n. Well, the first term is 1, second term is 1/2, 1/3, so on and so forth. Now, that would also, it turns out the left-hand rule, the left-hand rule with delta x being 1, that's our delta x, is exactly equal to this series. Well, notice that this is basically an overestimate of the area under this curve. So what does that tell us? That tells us that the improper integral from 1 to infinity of 1 over x dx is less than or equal to, and more likely strictly less than, we could say, this series. Now, I know it's been a while since we've done this improper integral, so we'll do it today just for some practice, but this is a divergent integral. And just as a reminder, what we do is we do limit as b goes to infinity of the now proper integral of 1 to p of 1 over x dx. And then we do our antiderivative. So limit as b goes to infinity of ln of the absolute value of x from 1 to b. Our limits are going to be positive, so we don't really need the absolute value. So limit as b goes to infinity of ln of b minus ln of 1. Ln of 1 is just 0. We're not concerned about that. This is the part we are concerned about. Natural log is an increasing function. It does increase slowly, but if you keep putting larger values in, you'll keep getting larger values out. So this goes to infinity. So this, we know that this improper integral diverges. We have something that is bigger than something that diverges. This is basically akin to our comparison test. So this series must diverge. So we know that n equals 1 to infinity of 1 over n diverges. Now, we don't want to have to set this up for every single one, but we can formalize this into one of our tests, and that is called the integral test, which is basically what we just did. You turn this into a function, you turn this sigma into an interval sign. This lower limit becomes the lower limit of your improper integral. Infinity is your upper limit. You calculate it. This is called the integral test. So basically, you know, we did it. I wanted to give you this example because we've done left-hand rule and I wanted you to see what was going on. You won't have to do this in the future. All you have to do is turn it into an improper integral, calculate the improper integral. If the improper integral converges, the series converges. If the improper integral diverges, the series diverges. So what did we do here? We turned it into an improper integral right here. We solved our improper integral, which we found was divergent. So this satisfies our hypothesis. So then we can say the series diverges, and we give credit to the integral test. Questions about this one? All right. Now, the integral test is on our sheet. It is on the second page. Did I miss it? I know it's on here. Here, right here, the integral test, bottom of the first page. Okay. Again, all the tests we're going to talk about today are on here. I just want to show you where they are. That is our integral test. So so with the integral test, if you have a series that it looks like you can take the antiderivative of the general term, use the integral test. And then all you do is turn it into an improper integral, and then you're back into our first module. Okay. Next up, let's talk about what I call p-series. Now, this is something that we talked about with improper integrals. Now we're going to actually formalize it and this is good integrals for good series for comparison. So we did this with improper integrals. Improper integral test will tell you what values of p these converge and what values of p they diverge. So when p is greater than 1, we just did the case where p equals 1. So we know when p equals 1, it diverges. When p is greater than 1 is when it converges. When p is less than or equal to 1, it will diverge. So there are two reasons that you want to be familiar with this. Number one, if what you are given is a p-series, for example, if you're given the series n equals 1 to infinity of 1 over n squared, p is greater than 1, this is convergent by p-series. And that's it. You are done. If what you have is a true p-series, it has to be in this form, but p-series is perfectly acceptable as a test. So this thing is convergent by p-series. Okay. This is on this sheet as well. Here it is in terms of improper integrals, but right here, here's the p-series, useful series for comparison. Okay. You can absolutely use that as a justification. But it does have to be a p-series. Now, what do I mean by that? Well, none of these are p-series. We'll come back to these. I want to see how much time if we have time left later, I'll come back to these. There's some interesting ones here. But we have a comparison test that we can use those p-series with. This is the exact same test that you had for improper integrals. If you have a convergent and you can show that the other series is less than it, then you can test for convergence. If you have a divergent and you can show the other series is larger, you can test for divergence. So they only work in one direction. So we do have to make sure that the hypothesis is met. Okay. So here's an example. Now, I want to point out this series is not by definition a p-series. We're going to have a pretty good intuition about it. It's going to behave a lot like 1 over n squared, but it is not a p-series because of that plus 1. So here's how we can leverage the p-series and the comparison test to show that this one is convergent. All right, so it looks like 1 over n squared. So just like our comparison test with improper integrals, we want to compare it to something known. So what we want to show, this thing is going to behave like 1 over n squared. So we want to show, remember we start at the bottom with these comparison tests, that 1 over n squared plus 1 is less than or equal to 1 over n squared. All right, we want to show a sub n is less than or equal to b sub n, because if b sub n converges, then a sub n converges. And then we work backwards. Let's flip them both. N squared plus 1 versus n squared. Now remember, when you flip fractions, you flip the inequality. And this is for n greater than or equal to 1. Where does that 1 come from? It's the lower limit. N squared plus 1 is going to always be greater than or equal to n squared. We have a very easily demonstrable true statement. So this one follows. And we've already shown that 1 over n squared converges. Then 1 over n squared plus 1 converges by our comparison test. Again, This comparison test works the exact same way as the comparison test for improper integrals. So if you were comfortable with that, for improper integrals, it's the same comparison test. Questions about this one? All right, and comparison test is on here. Here's a useful series for, there's a P series. Right underneath it is the comparison test. And right underneath that is the next one we're going to do, which is the limit comparison test. I actually really like this one, and I'll talk about why here in a second. I think it's a little quicker than the comparison test. So suppose that we have two series with positive terms. Then the limit as n goes to infinity of their ratio, if it comes out to a non-zero constant, then they either both converge or diverge. All right, so I'm going to show you, let's take a look with this first example here, how the limit comparison test works out. So we got this series of n equals 1 to infinity of 1 over, oops, 1 over n to the 2/3 plus 1. Okay, so anything that kind of resembles a p-series but isn't a p-series because of the plus 1, anytime you've got a polynomial over polynomial or n to some powers over n to some powers, one of the possibilities, good possibilities, is a comparison test. Now, we want to compare it to something similar. So you want to make sure that you choose something that to compare it to that is similar in nature, and what you look at are the lead terms of the numerator and denominator. So the series we want to compare it to would be n equals 1 to infinity of 1 over n to the 2/3. The reason we like this is because this is a p-series. In fact, it is a p-series where the p is less than or equal to 1. So we know that this guy diverges by p-series. So this is going to be the one we use in their comparison test. Now, first thing I want to point out about the limit comparison test, notice it's just a sub n and b sub n without the sigmas. And it doesn't matter which one you put on top. So I got limit as n goes to infinity, and I'm just going to use the general term, 1 over n to the 2/3 plus 1 over 1 over n to the 2/3. And our goal now is to calculate this limit. Now, the reason that choosing the one you compare it to is so important, if you don't make a good choice here, chances are you'll either get a limit of 0 or infinity, which is inconclusive. So that's why you always want to go, you want to look at your lead terms and make your choice that way. All right. Same thing we would do in a comparison test. Okay. Now, what we're going to do is we're going to simplify this as much as possible. Limit as n goes to infinity. We can flip this and multiply because we're dividing by a fraction. So we get n to the 2/3 over n to the 2/3 plus 1. Right now, we are in an infinity over infinity case. This allows us to use L'Hopital's rule. For some of you guys, it might have been a while since using L'Hopital's rule. It's not that difficult. Just what I do when I use L'Hopital's rules, I put an h over equals to let people know I use L'Hopital's. So that way you'll always be able to tell if you look at my work later. H over the equals on a limit means I use L'Hopital's. So what L'Hopital's says is we can take if we have our indeterminate form, infinity over infinity or 0 over 0, we can take the derivative of the numerator and denominator separately and then recalculate the limit. This is not going to be some nasty quotient rule because I'm just doing the limit of the numerator, or excuse me, derivative of the numerator, which is 2/3 n to the minus 1/3, over the derivative of the denominator, which is 2/3 n to the minus 1/3, because the derivative of 1 by itself is 0. Notice that I get the exact same thing. So limit of a constant is just itself, and then we recalculate the limit. This is a non-zero finite number. We already said this was, and we compared it to a divergent. So our series diverges by limit comparison test. So we satisfy our hypotheses. Number one, we need to compare it to something we know. So I picked a P series right here. Second part says we have to show that the limit of a sub n to b sub n goes to some non-zero finite number, which is what we did here, which allowed us to conclude that the series we were given is divergent, and then we give credit. Questions about this one? What I'll do is, depending on how much time we have left after I go through all these examples, you know, if there's time, if there's a test you want to see another version of, another example of, we can always come back and look at that. But I just want to make sure we have time to get through everything today. So I'll only be doing one example per until then. All right. Now, here's something interesting about this next series. Cosine, if you start putting in integers, some numbers are going to be positive and some are going to be negative. Notice that the limit comparison test requires the series to have all positive terms. So we can't use the limit comparison test on this one as is. So let's see what we're going to need in order to calculate this one. Because we do have a series that has negative terms. Also, this is not an alternating series. We're going to, you know, you saw the online lesson, and hopefully you guys went through the 8.4 as well as 8.3 for today. I know some people didn't, some didn't. We'll talk more about alternating series here in a second. This is not an alternating series. I'll talk more about why it's not when we get to that slide, but I just wanted to point that out now. It just happens to have negative terms. So here's what we're going to use. Convergence of absolute value implies convergence. So if we can show that the absolute value of a series converges, then so does the series. So we're looking at this guy. So we want to look at the absolute value. So if we look at the absolute value, what that does is that takes care of the fact that we had negative terms. And we know that cosine of n is always less than or equal to 1. So this sum is going to be less than or equal to the sum of 1 over 2n squared plus 5. All right, so this, we could do either a comparison test or a limit comparison test. Let's do another limit comparison test. We already know 1 over n squared is convergent by P series. So let's do a limit comparison test so we can see another example of it. So limit as n goes to infinity of 1 over 2n squared plus 5 over 1 over n squared. Flip and multiply to recalculate our limit. So we end up with n squared over 2n squared plus 5. Now, this limit can be calculated a couple different ways. One is we can say, hey, this is basically just a rational expression and just identify its horizontal asymptote. But I want to give you a little bit more practice with L'Hopital's because this is, n squared goes to infinity. 2n squared plus 5 goes to infinity. So this is another infinity over infinity case. We can apply L'Hopital's. So limit as n goes to infinity, we're going to have 2n over 4n plus 0. Those n's will cancel. The limit as n goes to infinity of 2 over 4 is 2 over 4, or 1/2. That is a non-zero finite number. So we know n equals 1 to infinity of 1 over 2n squared plus 5 converges. So our original series, cosine of n over 2n squared plus 5 converges by what I like to call the absolute value test. We took the absolute value, dealt with that, and showed that it converges. So, the absolute value test, convergence of absolute value implies convergence. So if you take the absolute value of your series to show that it converges, then what we have is convergence. And that's the absolute value test. Questions about this example? And, I didn't mention it at the time. I chose 1 over n squared to compare it to. I could have chosen 1 over 2n squared because that's 1/2 times a p series. But I mean, again, same idea. I'm looking at the lead terms of the top and the bottom to decide what p series to compare it to. The 2 I don't worry about too much. Like I said, we could say, okay, well, we could compare that to 1/2 times 1 over n squared. But 1 over n squared is going to do the job. That number is not going to make a difference in the convergence or divergence. This will work for some of our alternating series too. For example, we'll talk about alternating series in a second, but -1 to the n over n equals 1 to infinity. This is an alternating series because the terms alternate signs every single time. One way you'll recognize them right away is if you have a -1 to the n or -1 to the n plus 1, something like that. So that's going to be how you recognize it in closed form. But if we were to take the absolute value of this, the absolute value of -1 to the n over n squared, excuse me, that should be squared because I'm doing this example here. Sorry about that. Well, this is exactly equal to 1 over n squared from n equals 1 to infinity. This guy we know converges by p series. So we could say negative 1 to the n over n squared converges by the absolute value test. There's nothing wrong with that. That works perfectly fine. But there's another test that we can use when we do have what's called an alternating series. Now, again, for an alternating series, it does have to change signs every time. And this is an alternating series. So an alternating series must change from plus to minus every single time. The example we looked at earlier with the cosine, I'll just bring it up here. This one, 1 to infinity of cosine of n over, I think it was 2n squared plus 5. This doesn't change sign every single time because cosine of n isn't going to go through a bunch of integers. So this one is not alternating. Doesn't mean we can't write an alternating series in terms of our trig function, but it has to be properly written. And the one that would be an example, if it were this, cosine of pi times n, because now when this is 0, cosine of 0 is 1. When this is 1, cosine of pi, that's negative 1. Cosine of 2 pi is 1. Cosine of 3 pi, negative 1. Now this alternates. Okay, so make sure you recognize the difference, because this one we cannot use the alternating series test. This one we can. Okay. The alternating series test is pretty easy to use. Basically, all we need to say is that first, that it's alternating, and it converges if it's decreasing and the terms go to 0. So let's redo our example here with the alternating series test. So we'll do it in a different color. So now if we were to do this, there's two things we need to show. Number one, limit as n goes to infinity. And you only have to test the non-alternating piece. Don't worry about the negative 1 to the n. So we're only testing this part right there. That's going to be 0. And then the other thing that we need to show, well, let's see. We need to compare n plus 1, the quantity squared, with n squared. And again, this is for n greater than or equal to 1. Well, clearly, n plus 1 squared is going to be greater than n squared. Okay. Well, if we flip them both, we got 1 over n plus 1 squared is less than 1 over n squared. Well, this right here is a sub n plus 1. That's less than a sub n. These are the two things we need to show right here. That it's decreasing, and that the limit is that the limit goes to 0. So now we've already shown this, but I wanted to just show you the alternating series test. Is convergent by the alternating series test. Questions about the alternating series test. The first part, I think, is always really easy to show. You know, something we need to show anyways, right? Remember that theorem that gave us our test for our divergence test? We have to show that the terms go to 0. That's the same idea. The other thing is to show it's decreasing. What I would say for number 2, start with what you want to show and work backwards. We want to show this. Okay, well, what does that mean? This has to be less than this. Okay, well then flip them both and make sure we've got a very nice, obvious statement that makes sense. And there's our nice little proof. Questions about this one? I'm going to do one more time with the alternating series test because I want to show you something. We're going to do this guy. Slight difference, I've dropped the square, but it's going to make a big difference for what we're looking at. All right. So, new example. This is also an alternating series. Again, recognizable by that little piece up there. Okay, so we got an alternating series. First thing is if we tried to do the absolute value test on this. So let's say we try to do the absolute value test. Take the absolute value of -1 to the n over n from n equals 1 to infinity. This gives us our series that we have seen before. Guys, this one has a name. This is known as the harmonic series. You can Google harmonic series and get a whole lot of really cool information about this guy. Now, we've done this one before, but if we hadn't, well, we've got a p series, and the p is equal to 1. So we know this diverges by p series, which means the absolute value test is inconclusive. It can only test for convergence. So we need this one. We absolutely do have to go to the alternating series test. All right, well, it's alternating. Check. Limit as n goes to infinity of just the sequence part, not the alternating part, of 1 over n equals 0. Check. 2, very similar to the last one. N plus 1 is clearly greater than n for n greater than or equal to 1. So then 1 over n plus 1 is less than 1 over n. And that means a sub n plus 1 is less than a sub n. There's our two parts. So -1 to n to the n, over n is convergent by the alternating series test. Now, there's a reason I did these two, and it's because I want to, there's a contrast to them. You saw this in the online lesson. It has to do with what's called absolute convergence versus conditional convergence. If the absolute value of a series converges, then so does the series. And then we can say that that series is what's called absolutely convergent. All right, so this, when we did this one before, it was absolutely convergent. Absolute convergence is a stronger form of convergence. So because the absolute value was convergent, and actually this is all you have to test. Once you show that the absolute value is convergent, we can actually go a step further and say 1 over, let's see if I can make that a little bit neater. We can go a step further and say that our series is absolutely convergent. All right. Now we'll contrast that with the one we just looked at, our harmonic, well, the alternating series made up of our harmonic series. Because the absolute value diverges, we cannot say that this is absolutely convergent. What we can say is that it's what we call conditional inconvergence. So it's still convergent, but its absolute value does not converge. Again, absolute convergence is a stronger form of convergence. It's not difficult. Basically, all you have to do is take the absolute value of your series. If the absolute value converges, then it is absolutely convergent. And this is when you'll see it most often is with alternating series. If the alternating series is convergent, but it has negative terms in it, you got to take the absolute value and see if it's still convergent for absolute convergence. Questions about alternating series test or absolute and conditionally convergent? Usually it's pretty obvious when it's conditionally convergent because you're going to get a case like this. You take the absolute value and you're going to get something that, is like 1 over n or is a p series or it's very close to a p series that is divergent. All right. Then the next thing I want to talk about is actually not a test. It's the one, oops. But it's actually the error bound for an alternating series. All right. And the idea behind this is actually pretty cool. Let's see how well I can kind of represent it. So if we think about what happens, let's say we, with an alternating series, we start with a term, this is our a sub 1. And then we add something to it. All right, so maybe our first term is 0, and then we add 1. Then we subtract a half. Now our sum is going to be somewhere in between these. So that line is representing what our sum is. Then we add a third. Notice how it keeps crossing over. And this just keeps getting smaller and smaller. Well, what's happening is this means that our error in the first n terms can't be any more, is going to be less than the n plus first term. What does that mean? Okay, well, let's look at this guy. Here's our error. So we added, subtracted, added. So there's our error. This here, that is the n plus first term. And let me see if I can make this real obvious. We can see that our error is less than our n plus first term. Now, the reason that this is useful is when we have an alternating series, it makes it very easy to figure out how many terms we need to use to get within a certain tolerance. And I'll show you how to do that. How many terms do we need to get this series? So negative 1 to the n over n within 0.001 of its actual value. So what we want is to know how many terms will give us an estimate that is close enough to the actual sum. Now, once again, you do not need the alternating piece because all we're looking at is magnitude. So for this guy, our a sub n is 1 over n plus 1. Well, what we're going to use is a sub n plus 1. Whoops, excuse me. Sorry, I jumped ahead. Is 1 over n. We're going to use a sub n plus 1. That is the first unused term. We want 1 over n plus 1 to be greater than our error. Excuse me. We want that to be less than our error. So all we have to do is solve this. So we have 1 over 0.0001 is less than n plus 1. I might have added in an extra 0 there. So 1 over 1,000. And we want to solve that for n. So 1 over 0.001 is 1,000. We want n to be greater than that. So subtract off 1. So that means 999 terms is going to be enough to get us within this tolerance. This isn't going to be something we use a lot, but you know, we've done error analysis in here before. We did it with our numerical integration because we want to know how many terms do we need to get within a certain accuracy. Well, with alternating series, it's actually really easy because all we have to do is look at that n plus first term. So 1,000 is the first term to be less than this error. So we need 999 terms to get us within that tolerance. And again, this is just a little bit of informal reasoning behind it. What you need to know is how to use it. You look at the n plus first term. Do not worry about the alternating piece. You set it, you can set it equal to, you can set it less than or equal to your error tolerance solved, and that's going to be the number of terms. Questions about that? Okay. Now the stuff for alternating series. Here's the alternating series test. This is right here on the second page. The proctored exam won't have any error analysis on it, so that's why the formula that's why this isn't on there. Okay. One more test, but it's one of the biggest ones, most interesting ones, and very useful ones, especially going forward when we get into power series. We're going to do a couple examples of what is called the ratio test. Now, I'm not going to get into the derivation of the ratio test. It's done, it's done in the online lesson. It basically uses a comparison to a geometric series, which is why, just like with a geometric series, if the common ratio is less than 1 convergent, greater than 1 divergent, if you do get 1, the ratio test is inconclusive. And what I can say about that is that there's only certain tests that the ratio test works for, but the ones it works for, it works really well. First off, anytime you got a term that has an exclamation point in it, you're going to end up using ratio test. Now, this is not n yelling at you. This is what's called a factorial. So let's talk about what factorials are real quick. And you guys will get really good with these within the next week, I promise. All right, so a factorial means that it's the product of a number down to 1. So 5 factorial will be 5 times 4 times 3 times 2 times 1. So if you multiply all those together, you get 120. For those of you guys who've taken any probability or counting, you've seen factorials before. So when we have n factorial, that means we start at n and we go all the way down to 1. But we can't really say what it equals to because we don't know n. That's okay. That's not going to be important for our purposes. We're going to see next week or the week after when we look at Taylor series why the factorial has such a prominence. But it shows up quite a bit in some of the stuff we're going to be doing in Taylor series and power series. Real similarly, if we had what you do is you just start subtracting off 1 each time. So if you had 2n factorial, your first term is 2n minus 1 goes all the way down to 1. All right, and we'll see a few different, I'll try and hit a couple of different examples, and you'll see them in the homework as well. So you'll get some practice with the factorials. Like I said, you get good at them real quick. So let's talk about how the ratio test works. We'll do it with a basic example, then we'll pick it up a notch. So 1 over n factorial. All right, so here's how you do the ratio test. First, you have to identify that the ratio test is what you want to use. You see a factorial in there, you're pretty much for sure going to use the ratio test. So what we have to look at now is the limit as n goes to infinity of the absolute value of a sub n plus 1 over the absolute value of a sub n. I'm going to write it all out now, but I'm going to tell you some things that you can kind of shortcut or some things that you don't need to include as you get better with this. Number one, there's no negative term. So if you don't want to write the absolute value, you don't have to. But a sub n plus 1 goes on top. So for this one, a sub n is the 1 over n factorial. Then that makes a sub n plus 1 over n plus 1 factorial. So on top is 1 over n plus 1 factorial. On bottom is just a sub n. So 1 over n factorial. Now, every single time you do this, and this is why I'll skip this first step from here on out. The very first thing you're going to do is flip the bottom and multiply. Don't need the absolute values anymore. 1 over n plus 1 factorial times n factorial over 1. So from here on out, I'm going to skip right to this step here because it's always going to be what you do. You do a sub n plus 1 times the reciprocal of a sub n. And we'll talk about we'll do some other examples to see when we need the absolute value and we don't. Most of the time, you're not going to need them. It's just going to make everything positive. That's all. So if you had, if this were alternating, we wouldn't have the alternating piece in here because we'd be taking the absolute value. Okay, now here's the way these work. The next thing you do before you take the limit is you do as much simplifying as you can. Now, let's think about what n plus 1 factorial looks like. The first term is n plus 1. Then you start subtracting 1. So the next term is n minus 1, ... all the way down to n. Well, that is n factorial. And that's where you're going to see a lot of canceling when you have these factorials in the ratio test. So n, oops, wrote that backwards. So n plus 1, which is the first term, And then I'm just going to leave the rest as n factorial. We could write that out, but we don't need to. We only need to go far enough to get our cancel. N factorial cancels with n factorial. And so now all we have to do is calculate the limit as n goes to infinity of 1 over n plus 1. Well, this is a limit we should know. The denominator's growing, the numerator's not. This goes to 0. We check our conditions. If the limit is less than 1, our series is convergent by ratio test. And actually, I should probably write the series in there. Let's rewrite that. 1 over n factorial converges by ratio test. Because it's not this part that converges by the ratio test. It's the initial series that we're calculating. Questions about this one? We're going to do a couple more ratio test problems, but if you have specific questions about this one, let me know. We're going to do a couple more ratio tests and then see what kind of time we have left after that. And guys, I'm recording this, so this will end up, you'll have access to all this as well. Okay, now before we do some more examples, I want to just give you a quick rundown of how to decide which test to use. I tried to talk about it as we were going through them. Let me summarize. So first thing is, if we have a p-series, it's automatic. You can use the p-series test. Also, next is identify if it's geometric. You'll know it's geometric because the general term will be an exponential function. If it's geometric, all you need is the common ratio to be between -1 and 1. If it's similar to a geometric or p-series, use one of the comparison tests, either a straightforward comparison test or a limit comparison test. If the series happens to have negative terms, just take the absolute value, then use your comparison test. Never forget about the test for divergence. This is a quick one that can eliminate options very quickly. If the sequence does not go to 0, you already know it's divergent. If you identify a series as alternating, use the alternating series test. If you see a series with factorials and constants to n power, use the ratio test. So now this would be a constant to the n power, but it doesn't have any factorials. So this, we would just use geometric. I'll show you one in a second that has both. Lastly, if it looks like you can take the antiderivative of your general term, use the improper integral test. All right. I gave you the link to this PowerPoint in the meeting invite today. So feel free to, use this as a guide as you're going through the homework. Here's some examples. Let's see what we can get through. I think we got enough time to get through a couple of these. Let's see how it goes. The first one we already did, so they were already good. So let's go to the next one. So we have the series of 1 over 2 to the n factorial. All right, so this has a combination. The 2 to the n, if it were just this, 1 over 2 to the n, that is geometric. And it's got a common ratio of 1/2, so it converges. And so converges. All right, but we have that extra n factorial. So that's where the ratio test comes in. So because we're still learning the ratio test, let me bring it up. All right, so we automatically go to the ratio test. So we're looking at the limit as n goes to infinity. There's no negative here, so you don't have to worry about the absolute value. And like I said, I go right to the fact that it's a sub n plus 1. So you're turning all your n's into n plus 1s. And then the reciprocal of a sub n. 2 to the n factorial over 1. So now we're going to look for any canceling we can do. And this is going to be canceling you're going to see a lot, especially in the ratio test going forward, because we're going to see it in power series. We've already seen how to rewrite this. This is n plus 1 times n factorial. Here's one that we haven't talked about yet. 2 to the n plus 1. Well, that's 2 to the n times 2 to the 1 by properties of exponents, or 2 to the n times 2. You're going to see that happen on a lot of these. So 2 to the n times 2. What's really nice about the way it's rewritten, our cancels become very obvious. The n factorials and the 2 to the n's. That 2 is a constant. And one of the things you're going to see me do, and this is going to be more useful when we get into power series. It's not as big a deal right now, but I'm going to pull that 1/2 out front. That's basically pulling that 2 out front. And I get left with limit as n goes to infinity of 1/2. Oh, no, sorry, I jumped ahead. Excuse me, guys. 1 over n plus 1. That limit goes to 0, which is less than L. So our series is convergent by the ratio test. And that is how the ratio test is used. Questions about this one? Let's do one more ratio test. This is an interesting one. This is a tough one. Not one I would give you on an exam by any means. Could, maybe take home problem level, or it could be a homework problem level, but this last one here. I like this one. There's some interesting stuff going on in this. But I wouldn't expect it to be obvious unless you've seen how to handle something like this before. So this one gets a little messy because we have two things going on. We've got a factorial on top and an exponential on bottom. And so the question becomes, does the factorial or the exponential win? And especially in n to the n case. All right, so let's set up our ratio test. Ratio test for you. Limit as n goes to infinity. Everything's positive, so I'm not worried about the absolute value. Basically, you're going to add 1 to n. So n plus 1 becomes n plus 2 factorial over n plus 2 to the n plus 1. And then times the reciprocal. N plus 1 to the n over n plus 1 factorial. Now, as we said before, our next job is to do some of the math on this, see how much we can simplify. Well, we're going to do a lot of the same factoring we've been doing. So n plus 2 factorial is n plus 2 times n plus 1 factorial. Because n plus 1 would be the next term, n the next term, but we only need n plus 1 factorial for our cancel. This guy, n plus 2 to the n plus 1. I'm going to do something similar that we did before. That can be rewritten as n plus 2 to the n times n plus 2. That's the same thing that I did with 2 to the n plus 1 in the last one. This is like to the first, those exponents add. Not much we're going to do with this other one. N plus 1 to the n, and then n plus 1 factorial. This is the fun part. Once we set up our cancels, we get to do a whole bunch of crossing out. Now here's where this one gets really interesting. So here's where we're at. We've got limit as n goes to infinity of n plus 1 to the n over n plus 2 to the n. Well, two things to the same exponent, we can write those to the same exponent. In other words, limit as n goes to infinity of n plus 1 over n plus 2 to the n. Now, what happens inside here, this goes to 1, n goes to infinity. So what we have is a 1 to the infinity case, which actually qualifies for L'Hopital's. Now, before we use L'Hopital's, we want to have 0 over 0 or infinity over infinity. So let me show you how this works. So what we do is I'm going to let this expression here be L. So L equals n plus 1 over n plus 2 to the n. And I'm going to take the natural log of both sides. So what we're going to do is we're going to rewrite this so that we don't have that n up there. And so what I'm going to do is actually find the limit of the ln of L, and then we'll convert it later. So what we're going to look at, and I'm not going to write in equals because these aren't exactly equal. What we're solving for is the ln of L. Again, not obvious if you haven't done it before. I just wanted to go through this one with you, just so you can see a really interesting example of how interesting these limits can get. Now, right now, this goes to 1. Ln of 1 is 0, and that is infinity. So this is an infinity times 0 case, which means we can rewrite it as a L'Hopital's. So limit as n goes to infinity. It's probably easier to leave this up on top, ln of n plus 1 over n plus 2 over 1 over n. So I didn't change anything. I took this n and rewrote it as dividing by 1 over n. Think about going the opposite direction. If we flip and multiply by the n, we end up here. We now have a 0 over 0 case. I can use L'Hopital's rule. But I'm going to make one more step before I do use it. And that is I'm going to rewrite the numerator using a property of logs. Not that we have to, but it'll make the derivative a little bit easier. Property of logs says I can rewrite that numerator as ln of n plus 1 minus ln of n plus 2 all over 1 over n. Now, we can apply L'Hopital's. Means I'm going to take the derivative of the numerator and denominator separately. Can't emphasize that enough. So the derivative of ln of n plus 1 is 1 over n plus 1. Derivative of ln of n plus 2. Now you can see why I use that property. It makes those derivatives quite a bit easier. And then derivative of 1 over n is negative 1 over n squared. All right, now what we want to do is simplify and see if we have something that is a little bit easier to deal with than what we had. So I'm going to find a common denominator and add those fractions together. So because of time's sake, I'm going to go a little bit quicker on this one. What we're going to end up with is n plus 2 minus n plus 1 all over our common denominator. So that's just adding those two fractions, n plus 1 times n plus 2. Find the common denominator, subtract the two fractions. And instead of dividing by 1 over n squared, let's just multiply by negative n squared. We don't need to keep the negative because we're going to be doing absolute value. Equals, actually, we do need to keep the negative because we're doing ln. All right, so let's see what happens here in the numerator. Limit as n goes to infinity. So we're going to have a negative n squared times n plus 2 minus n minus 1 all over n plus 1, n plus 2. Now here, n minus n, those cancel. 2 minus 1 is 1. So negative n squared times 1 is negative n squared. So we have limit as n goes to infinity over negative n squared over n plus 1 times n plus 2. Now, if I were to FOIL this out, I would have an n squared as my lead term on bottom. So knowing what we know about rational expressions, I've got an negative n squared over an n squared. We could also do L'Hopital's, but I know we're running low on time. This limit is going to come out to be negative 1. Now, I didn't find the limit. I found the natural log of the limit. So the natural log of the limit is equal to negative 1. How do we get that out of a natural log? We make both sides exponents of e. And we end up with our limit equals e to the negative 1. That's important because e to the negative 1 is less than 1. So our series is convergent by the ratio test. So that tells us that n to the n goes much quicker than n factorial. Now, I'm not giving you this example to scare you. You're obviously not going to be doing a bunch of these in the homework. And like I said, I would never give you something like this on a proctored exam. It just takes way too long. But I just wanted you to see, first off, I wanted you to see another example of the ratio test. And then I wanted you to see one where, okay, maybe initially it's not easy to tell what the limit is, but based off of what we know about L'Hopital's rule, which is the part in purple here, we can calculate that limit. Now, one of the things you can do as you're going through homework is you can use other means to help you calculate limits. What do I mean by that? Well, Wolfram alpha can calculate limits. So limit of, let's see how we do on here. So this was the limit that we had to take right there. So let's go with that. N plus 1, so 2 sets of parentheses. N plus 1 by n plus 2. N plus 2 to the n as n goes to n. And there is our limit of 1 over e. So I don't want you to think you're out there without a life, okay? Check this limit first with Wolfram to see if you should try it by hand to see what you should get, okay? Again, this is kind of a tougher example. All right. Now, we are about out of time.